So, what I want to first start off with is showing you the workbook that you'll be using to learn these materials. I'm using the textbook called Active Calculus, which takes a very different stance than your usual textbook. It invites a lot more active engagement, working through problems, open-ended questions. And what I really like about this book is that it comes with a blank workbook for you. So there's a PDF linked in Module 1, as well as the answers to the questions. And there's also a printout. If you wanted to buy it on Amazon, there is a link for that if you'd prefer like a hard copy. But it's a very interactive book, and we go in deeper on the fundamental ideas instead of kind of a more scattering of different types of problems that we'd see in maybe your typical calculus book. So the invitation here is to work along with me through this first video. I'll be using this here and there in my lecture videos in general, but for this first one, I just wanted to kind of introduce you to this document, as you'll be, watching my lecture videos for kind of like high-level insights and concepts, a bit more of the professorial thing, and then working through these as your activity, kind of like a lab would be, and then pairing that with, your homework or your critical practice assignments. All right, so enough about the framing. Our first chapter is understanding the derivative. Okay, so we're going to first start off with this idea of recalling how do we measure velocity, and let this drive us to the derivative function, which is really the big idea of this course. Okay, it is the biggest thing that we'll be studying. So I like the fact that we'll just be jumping right in. Okay, so starting with chapter 1 here, 1.1, how do we measure velocity? You have a preview activity. And so this is to kind of jumpstart your brain to get the prerequisite knowledge flowing. So what I'm actually going to do is I'll read through this with you, and then I want you to hit pause on the video so you can work through it. Again, you got to get your hands dirty. You can't really learn this passively. And then when you're done giving it a shot, it might not be perfect, you can hit resume and we'll go through it together. Okay? So let's suppose that we have a ball that has a height s at time t, a function of time, and it's given in feet by this formula. So we're going to construct a graph and label 6 points, including when it reaches its highest point, when it lands, and when it's launched. Describe the behavior of the ball on 2 intervals, and then consider this average change expression and interpret what it means. Okay, so again, this might take you 10 minutes that you have me on pause, and that's okay. And then come back, and then we'll go through it together. All right? All right, so I'm going to be using Desmos a lot to graph and do calculations. One main reason is because it's just a lot easier to use on the PC where I'm recording these. But also, I think it's a little bit more intuitive than your TI-84, but you're welcome to use whatever graphing utility you'd like as approved by the syllabus. There's a few things that are restricted. But here, I've graphed this function. What's nice about Desmos, I can preserve the variable name, so I'm using t as long as I define it like this. And so I've got a graph. I changed the window so it's a little bit better to see. And now I can grab some points. This will actually automatically grab some intercepts as well as the local extrema, so this apex here of the ball being thrown. I know that this is happening at t equals 1. This is where the ball was launched, right? At t equals 0, this is the height. And at t equals 3, the height is 0. What does that really mean? It's where the ball, right, hits impact on the ground after 3 seconds. So this activity actually asked for 6 points. So you can actually go in and find a few more. So we might find, s of 0.5 might be a good one. That's at 60. You might find s of 1.5 and maybe s of 2.5. That'd be 6 total points. Okay. So I think we've satisfied everything for that first one, labeling these 3 distinct points asked for. And so let's take a look at the behavior of the ball here. Okay, so it's asking for the behavior of the ball on time intervals 0 to 1, and then from 1 to 3. And it's asking what happens at t equals 1. So let's actually go back to our graph here. So between 0 and 1, let's take a look. I can find s of 0. I know the height is 48. I know that height at 1 is 64. So what's happening between here and here is that the height of the ball is increasing, and we could even, describe how fast that's increasing, perhaps, using the average rate of change. And then from 1 to 3, so we could take a look at what's happening at 3. We know the ball has hit the ground here, so we would say that the height is decreasing from 1 to 3. So it's ascending in the air from 0 to 1 seconds, and from 1 to 3 seconds, it's descending to the ground. Okay. So what occurs at the instant t equals 1? Well, this is that moment where the ball reaches its apex, and then gravity takes over, right, and then starts pulling it back down in the opposite direction. So it actually stops its trajectory for a moment and then starts descending. So lastly here, we're asked to consider this expression, which is the average rate of change, or average velocity here, since it's in a position and time context. So compute the average velocity from 0.5 to 1. What does this measure on the graph, and what does this tell us about the motion of the ball? So from 0.5 to 1 is really talking about from here, this point, to here, this point. Okay. And so we're looking for the, that was a little wacky. We're looking for the rate of change, the delta S over the delta T of this window here. Okay. So if we go ahead and calculate this, so S of 1 minus S of 0.5, so that'd be 64 minus 60. I'm just grabbing these off this table here. So this would be 64 minus 60, S of 1 minus S of 0.5, over 1 minus 0.5 is 0.5, which is 4 over 0.5, which is 8. Okay, and what are the units here? This is important. Well, the units bear the units of delta S over delta T. This is measured in feet, and this is measured in seconds. This is feet per second, which makes sense. What is the rate that the height is changing? That's going to be in feet per second, like miles per hour. It's a rate of velocity. So what does this tell us about the motion of the ball? Well, we can be pretty specific here. This is changing at a rate of 8 feet per second, but changing is kind of general. What do we know about it? It's going up. And that's actually denoted by the fact that it's a positive 8, not a negative 8. So the height is actually increasing. Height is increasing 8 feet per second between t equals 0.5 and t equals 1 second. And I'm going to put in this little qualifier here, on average, because we're using the average rate of change. So we know it's got some curve to it, so it's not actually just this flat, constant rate. And then what are the units? We know that this is feet per second. All right. So in general, these preview activities are going to kind of get you framed up and ready for the kind of lab of the section. All right. So let's move on to the actual activity here. Okay. So here for this first lab activity, we've got the same position function, that same ball that's been tossed or launched. It's 48 feet in the air. So we're going to compute the average velocity on the following intervals. This is something I'm going to have you do, and I'll have you check again to kind of reinforce where these things are, that the solutions are in Module 1 to this. So look for activity 1.1.2 to verify that you got the right average rate of change for each of these intervals. Okay, you should see that they are each approaching a certain value. Okay, and that value is 6.4-ish. And so then on part B, we're going to look at this particular set of points from point A to point B. What is the slope between these two, and what does this mean? And then we'll keep going from there. But first, what I want you to do, I'm going to give you, again, 5-10 minutes and go through and compute these average rates of change to get used to this. Hit pause and then come back, okay? Okay, so I know I gave you the answer. It should be 6.4, but again, trusting you to take ownership and agency of your learning here and do this, because we won't learn this passively. So again, each of the units there should be feet per second. So for part B, what do we see? We've got these 2 points, and if I ask what is the slope of the line between these 2 points, okay, what does this really mean? Well, in some ways, it's just, you know, a line connecting 2 points through a curve. We call this the secant line. Which just means that it touches in 2 places. But it also represents the fact that the slope between these 2 points is what? Delta S over delta T. So M, or slope of L, is the average velocity from point 4 to point 8. This is a key idea. Okay, there is this connection between the abstract, the geometric slope, and the average rate of change, the physical context. This is going to keep happening throughout the course. Okay. So in light of this meaning, what is a geometric way to interpret each of those values we did before? So for each of those average velocities that you calculated, these are also the slopes of the line passing through those 2 points on the curve. And so what you're approaching with each of those, if you did it correctly, is something like this, where you're starting with this point, going through the slope of that point, and here at point 8, right? They were kind of all centered around point 8. And then we were scooching those points closer and closer. And then same from the right-hand side. And so what was actually happening is you're kind of getting closer and closer to maybe a line, the slope of the line passing right around that point B. Okay. So what it's asking now is to zoom in around the point containing the value t equals 0.8 and see what happens. So let's go ahead and do that. Let me plug in, x equals 0.8 to give us a place to zoom in on. Let's see what happens. All right, so this is the point I care about. We see this curve's got some bend to it, and the closer I go in on this point, what seems to happen? Well, I've kind of like cut out the distractions of the preceding and following moments, and I'm just getting closer and closer to t equals 0.8, and this curve starts to look like a line. And this, again, is a key idea. The fact that if we can zoom in on a function that's relatively reasonable, that it will start to look linear. And what do we know about linear functions? They're super simple. Okay, and so this is part of what I was talking about before of slicing things into smaller, simpler problems. If we zoom in very, very far, we see, hey, things start to look linear, and lines are easy. I just need a point and a slope, and I've got that thing figured out in that little region around it. So this is what we want to reflect here in our notes, that when we zoom in closer and closer, we see that starts to look linear. Okay, and now it's asking, what do you conjecture the velocity of the ball is at the instant t equals 0.8, and why? Okay, so this is kind of a paradoxical question because you're talking about an instant and velocity, which requires change. But, right, if we were to just get a snapshot of how fast is it moving at t equals 0.8, what would you think it is? Well, in your part A values, you should have had something like 6.41-ish and 6.38-ish coming from both sides. And so we might say, it's around 6.4 feet per second. And why do we think so? Well, because as we zoom in further and further, those slopes of the secant lines are going to start to converge to this one slope. Another way you could view it too is if you went to this graph and maybe grabbed 2 points off of here and saw what the slope of this seemingly flat line would be, this might give you something very, very close to 6.4. So I'll leave that to you there. Okay. Okay, and this next activity, I'd actually encourage you to do this on your own. It is going to kind of investigate the meaning of the sign of the instantaneous velocity and it's a extension of what we just did. So I'm not going to do this here in this video. What I do want to do is let you do that, hit pause again, then come back, and we'll work on this last one, because this has a bit of algebra that's going to persist through the unit, and I think it'd be helpful for you to see me do this out. So for this function, again, find the most simplified expression you can for the average velocity of the ball in the interval from 2 to 2 plus h. Now, what is this h? You can kind of think of h as like a nudge. Okay, it's a little discrete change in the variable. So we're talking about in the average velocity of the ball from t equals 2 to 2 plus a little bit. Right? And that h is just that little bit. And then use your result to compute the average velocity on 1.5 to 2 and estimate the instantaneous velocity at t equals 2. All right. So let's go ahead and just grab this simplified expression for average velocity. So average velocity from 2 to 2 plus h is equal to s of 2 plus h minus s of 2 all over 2 plus h minus 2. Okay. And so let's go ahead and work a few of these out separately, because it's going to be a little bit of work. So s of 2 plus h, what is this? Well, it's going to be 64 minus 16 times, wherever I see t, I'm plugging in 2 plus h. All right, so on the inside here are these brackets. 2 plus h minus 1 just becomes 1 plus h squared. Square this out. You might want to say 1 squared plus h squared. It is not, right? Remember, you have to double distribute that through, so it becomes 1 plus 2h plus h squared. Would do you well to review why that is the case if that comes as a shock. Then distribute that 16. And then we can simplify a bit further. So this would be 48 minus 32h minus 16h squared. All right, so that all works out to be that middle part. We know what s of 2 is, don't we? S of 2 is 48, isn't it? Let's pause here quick. Yes, s of 2 is 48. So we know that from our graph. And in the bottom, 2 plus h minus 2, it just leaves us with h. So this whole thing reduces to 48. Let me keep the colors here. 48 minus 32h minus 16h squared minus 48 all over h. And so what happens is these 48s cancel. You're left with negative 32h minus 16h squared over h. And so we can, and please only do it this way. You will save yourself much heartache in this course if you factor out the h on top before canceling. Okay, and we're going to do this a lot, so you'll have a lot of chances to practice that. But if you do it the shortcut way, man, you're going to have a rough go. I see it flop all the time. So this is the expression we get for the average velocity between 2 and 2 plus h. Okay. Now, what the question is asking is use this result to compute the average velocity on 1.5 to 2 and to estimate the instantaneous velocity at t equals 2. So this is the velocity you'll get from 2 to 2 plus some nudge in h. All right. So here, what would the nudge be in order to find the average velocity from 1.5 to 2? Well, this would be negative 32 minus 16. And what was the nudge for 2 to get to 1.5? It was negative 0.5. Okay. And so this will end up being, what, negative 32 plus 8, which is negative 24 feet per second. All right. And so is that a good estimate based on what we have? You can go to your graph and see, but it should line up. Okay. So now it's saying use this to estimate what the instantaneous velocity would be at t equals 2. Well, what does that mean, really? Well, what we were doing before was kind of inching in with our average rates of change to this point. And so here we've got this, this shrinking happening from just this nudge h. Okay, this is the difference off the point that I'm taking that slope from, before and after. So wouldn't the idea be to take h as small as I can get it? So maybe let h be, I don't know, 0.01, or let h go to 0. And then what do we see? We see, well, maybe the instantaneous velocity at 2. Let's write it like this. At t equals 2. Does this equal negative 32 feet per second? And so this is a good impulse. And that's actually the right thought. But the issue is right here. The fact that we are dividing by h this whole time. If you let h go to 0, what happens? This whole thing blows up. One of the core issues in math is that we can't divide by 0. That's an undefined operation. So that's an issue that we're going to unpack later on. But this is the direction that we're heading, moving towards how do we measure velocity or the rate of change at a moment, at an instant in time, without this paradox, without this conflict of the fraction blowing up when we do it. Okay. So after this, you've got a set of exercises to extend and unpack what we just discussed. This isn't going to be enough to really kind of do these ideas justice. So a few of them are interactive in the text, and a few are just out on pen and paper. Please do them all in your notebook, whether it be here in this workbook or on separate paper. But you're going to want to have these for reference for me to check in on later and for you to study from for your test. So don't just enter them into the computer and have them disappear into the void. Okay. So I hope you found this helpful, and I will see you in the next video. Make sure all questions on this and your exercise set go into the class discussion so we can all benefit from that Q&A. Awesome. Have some fun.